Okay, last time we already go to this thing, full wave rectifier. Okay, so basically, if you're looking at the input to get the peak to peak will be 200 volt. Okay, and the ratio for the transformer 2 to 1. So that means the voltage, okay, across the secondary supposed to be how many volt?
100.
100 peak to peak.
Yeah, just a minute, okay? Okay, so that will be output here, input output. So the secondary will be 50 volt, okay? So they can get a 25 volt peak. Okay, so the output, they will be, V peak will be 24.3 volt. The output will be a full wave rectified. That means they can rectify for positive. Also, they can rectify for negative. So that's why we call full wave. And the voltage peak for the output will be 24.3 volt. How come you get 24.3?
Minus 0.7.
Exactly. The thing is you get the output, they can get both AC and the DC. The diode will be on, so that's why they get minus 0.7 volt. If you want to measure from the V peak, you have to measure from 0. So that's why you have to take 25 volt minus 0.7. You get 24.3 volt. And the next one, also this full wave rectifier. That means they rectify for both positive and negative the same thing, like the one we just done it. However, this one they just using the normally transformer, not center tape. Center tape transformer cost a lot of money. So that's why they're using the bridge rectifier, just a 4 diode. A diode maybe cost 25 cents, say a lot of money, and they working will be same thing. And the same thing, they can say right here during the positive half cycle. So this one and this one will be on. Okay. Now, how come? The thing is when you get a positive coming in, so the positive on this side will be turned on D1. Okay. They will be turn it on D1. How about the D2? How come the D2 can be on? You understand you get positive on this side here. Okay, that's easy to recognize D1 must be on. And now, how come D2 be on?
By the second half of the signal.
Okay, you understand when you apply the positive on this side, okay, this side positive and this side will be negative. And when you get a negative in here, and this is a 0 volt round in here, So that's why turn D2 on. So you get a D for the first cycle positive, you get D1 on and D2 on. However, for
Is
the
this,
second,
sorry, is this AC voltage?
what do you mean? What voltage?
I'm just wondering if it's the reason why the second diode open and the negative is flowing. It's because it's AC and DC and not
Okay,
DC.
what I'm saying here, when you get a positive here on this side,
Mhm.
what on this side?
That should be the negative.
Okay, this is a negative and you get a round on anode D2. So D2 will be get going this way. So that's why they will be on. I try
Okay.
to explain to you how come D1 be on and D3, D2 will be on.
Okay, I see. I see.
Okay? When you get a negative cycle in here, this have to be positive. And this positive turn on D4. Okay? And this side negative will be turned on D3. The thing is you get a round right here. Okay?
Got it.
That's why you can get full wave rectifier right here. Okay? And also they try to explain to you, during the negative half cycle of the input, D3, D4 are forward biased, and the conductor current, D1, D2 will be reverse biased. Yeah,
So it acts like a series circuit and not a parallel?
this is hard cannot telling you series or parallel. Okay, which one is series or which one is parallel? I try to explain in here, telling you for the first positive on this side, okay, right here, positive here, on this side, then D1 must be on. However, D3 must be off. Why? You get a round on this side and a positive on this side, D3 will be off. However, when you get a positive on this side, then also at the same time you get a negative on this side. When you get a negative on this side here, and this will be a 0 volt round, this D2 must be on. Okay? And the D4 must be off. They just try to explain to you which diode will be on the positive cycle and also on the negative cycle. And also they already explained to you in here, during positive half cycle of the input D1, D2 forward bias and conduct the current. However, D3, D4 will be reverse bias. And now they given you another one, another half cycle here. That means if you get a negative on this side, then this side must be positive. Okay? If you get a negative here, okay, and you get a negative here, D1 must be off. Okay, the thing is that will be round. And D3 will be on now. The thing is round right here and a negative on this side. Also, if you get a negative on this side here, okay, let's see, you get a negative on this side, you get a positive on this side, turn on D4. Okay, only thing is make sure you understand which diode will be on, which diode will be off, depending on positive here then negative here. That's only thing. Okay, on this circuitry, not like the DC circuitry, we cannot tell series or parallel. Okay,
Okay,
any
thank you.
question? Now, for the practical diode, that means second approximation, VD equal 0.7. And if you want to calculate the V peak output, this is the formula. Okay, equal V peak of the secondary minus 1.4. Why they minus 1.4?
Because two diodes.
Exactly. One diode 0.7. Two diode will be minus 1.4. Okay, so now let's see. For the bridge rectified circuit below, transformer specify a 12 volt IMS. Okay. $12 volt IMS secondary voltage for the standard 110. That means you get 110 volt here. And basically on this voltage, they already gave it to you, 12 volt. Okay. That's why they not giving you the ratio here. And they want to know what we peak, telling me what we peak equal. You do a
110.
calculation for me.
110.
What I saying here, the voltage is a secondary 12 volt RMS, right? VP second.
Minus 1.4.
No, you have to divide the VRMS divide by 0.707 to get the peak, and then subtract the two diode drops.
Okay, they want the output will be peak output voltage, right? In order to get a peak output, you need to get the VP second. V peak second equal 12, right? RMS divide. Okay, to see what you get.
16.97.
You get 16.98, 16.97. V peak. Okay, so the voltage V out peak, we already know. V out peak equal what? V second, right?
Yeah.
V peak of the second minus what?
1.4.
1.4 volt. That's just the formula. Okay. So basically, you can get the peak of the out equal 16.97 minus 1.4 volt. Try to really understand, okay? Anything else You not quite follow it. Just go ahead and ask the question. Okay, let's see. Capacitor input filter. Now, let's see where we are now. Okay, let's see. Okay, I want to get a little more detail for you about a capacitor. Okay, the symbol is C, right? Unit a farad. Okay, and capacitor will be look like. Now, normally you get a farad and you get a milli. Farad, you get a micro. Farad, nano. Farad, picofarad. Okay, milli will be 10 to a minus, right? Micro. And also minus 9 and minus 12. This is a table we already given to you. When the capacitor connects into the AC circuitry, so it has the resistance. Will be called capacity reactance. HC. Who know the formula?
1/2 pi FC.
1 over 2 pi FC. So when you connect the capacitor into the AC circuitry, and now the capacitor will get a resistance, but they not call a resistance. They call a capacity reactance. And they will be calculated by HC equal 1 over 2 pi FC. In this formula, Xc will be in O. You know pi 3.142. F must be in Hertz. And capacitor must be in Farad. Okay? So you understand the capacitor will be, if they connect into the AC circuitry, they get the resistance. And that resistance will be calculated by Xc equal 1 over 2 pi Fc. And now we can say at DC, what the frequency equal?
0.
For the DC, what the frequency equal? How many hertz?
0.
Perfect. 0 hertz. Okay, so now I can calculate Xc 1 over 2 pi Fc. And F equal 0. So 1 over 0 equal what?
Infinity.
Perfect. Infinity O. That means they will be out open. So for the DC, capacitor will be open. That only telling you they not allow the DC current flow through the capacitor when they be full charge. They open. Okay. And now if I say at AC, what the frequency equal? So basically for the AC, you can say frequency equal 60 hertz. Okay, or 1 kilohertz, 1 megahertz, any. So basically I using this number, so nobody can say bigger. Infinity hertz. It can be any frequency. Okay, but I using equal infinity hertz. It's a maximum. So I can say Hc equal 1 over 2 pi Fc. Anything multiplied by infinity, you get infinity. Equal what?
0.
Perfect. Okay. Equal 0 ohm. 0 ohm means it's shorted. Okay, so Ic will be shorted. That means like just a wire. So that's the two things you must be memorized. Okay. To the capacitor, it's a DC, they open. However, for the AC, they just like the wire, they short it. Okay. If you done for take the note, let me know, I erase it. The thing I basically did will be going to the AC circuitry, offer only on the summer, but really we need it for electronic side, so we need a few things we must know in the basic. So we go to that thing here. I make sure you understand the capacity reactant formula. Okay. And also make sure for the DC, capacitor will be open. Do not allow DC current flow through capacitor when they full. And for the AC, they short it. They just light the wire so the signal can go.
But Mr. Pham, isn't it also true? I mean, it's not true that for every AC, it's a short circuit, only for very high frequency.
Doesn't matter on the basic. They don't have to be high frequency. Any AC, capacitor light the wire. So after that thing, then we'll go a little more on the capacitor will be charging or discharging. Okay, you already done?
Yes, sir.
I erase it. I need the rule. Okay, so now we're talking about capacitor when they're charging. Okay, they will be charging this way. Keep going up to the point. That means the maximum here. VC, for example, 12 volt. So basically they start charging going up. Maximum is 12 volt. Okay, and they stay at the 12 volt. You understand in your car battery, inside the battery just the capacitor. Okay, so when they get a problem, they don't have enough 12 volt. So you have to bring that battery to the auto park. How long take them to charge it for you?
All day.
It depends on how much resistance is in series with the capacitor.
Normally. For mine, I already did it. Take 24 hours. Okay. The thing is that telling you, they will be charging up, but very slow. Okay. Until they full charge. That means 12 volt. And if you see the circuitry here, when they're charging up, we get a one we call a tau equal R times C. That's what we call a time constant. In this formula, R must be in ohm. C must be in farad. Okay, now what is the definition for time constant? Who knows?
Speed of light.
The time to charge at 63% of the total.
Perfect. Okay. That means the time to charge up to 63.2%. Okay. That means if I say right at this point right here, you going down for the time, you get time constant, and the voltage here will be 63.2 times 12 divide 100. That's a basic definition for the time constant. That means the time for the capacitor charging up to 60.3% of the maximum value. In this example, maximum will be 12 volts. Okay, so one time constant, they can charge up to 63.2 times 12 divided to 100. Then you know what the voltage.
Does 100 come from 100%?
Right,
Okay.
that's what we say percent, 63.2%. And also they say after 5 time constant, capacitor must be full charge. So that only telling you the capacitor charging, they cannot go directly quite right away to 12 volt. No, take your time.
Can you explain how the current behaves?
What?
Can you explain how the current behaves?
You can see the current will be flowing this way, right? They will be charging up.
But yeah, the initial current will be high, but the final current will be 0.
Yeah, when they full. The current, depending on 12 volt, whatever current you get, when they charging up, when they full, then the voltage across the capacitor here also will be 12 volt, right? When they full charge. So you get a 12 volt on this side, 12 volt on this side, the current will be 0. Okay, you done? And the last one. Okay, after you done, let me know so I can move on. Okay, so this will be charging. And we get the last one will be discharging. Okay, now we're talking about discharging. Okay, you start from 12 volt. Okay, like exactly when you turn on your headlight on your car and you forgot to turn it off. Now the car battery will be discharged. Keep discharging. Okay, so this will be discharged. Okay, so if you take about couple hours or one day, your battery will be empty. So this will be a discharge. Same thing. They cannot discharge right away to zero. This will be take the time, depending on the time constant. Okay. That's why, from my understanding, if you get a car, you're not driving for a while, then how come we can keep your battery still okay?
Unplug it.
And plus, what?
Unplug the positive and negative.
No, we don't have to. Maybe I'm not right, but I can tell you. You just remove the black connection. So capacitor cannot discharge.
You're saying remove the ground wire, right?
Right. That was black one. That is capacitor inside battery cannot discharge.
Makes sense.
Yeah, that's what they told me.
Actually, I think either terminal will work.
But
turn-
normally you don't want to touch for the positive. You brown the black one more easier to remove out.
or turn it on every other day and run it for 10 or 15 minutes.
That's what I have to do now. The thing I'm not driving. Okay, let's see. We try to finish this thing, okay? This week we try to working with the bipolar transistor. Now, this one they're talking about input filter. Okay, if you're looking into here, you can see for positive, capacitor will be charging up. See that? So when they get a negative cycle, capacitor will be discharged. However, they discharge not down to zero, and they go charge again. So that's why. Okay, the capacitor charge back to big peak of input when the diode become forward bias. Discharging occurs during the portion of the input voltage indicated by the solid blue curve. Okay, so this is a charging. This will be discharging, but they cannot charging down here and they charge again. Okay, so they discharge just a little and they keep going. Now you can see that this is positive, they charging up. Okay, and this will be discharging. Okay, and small, that's what they call a ripple. Okay, ripple, that means the noise. Okay, we don't want that to be. So smaller ripple means more effective filtering. General, the larger the capacitor value, the smaller the ripple for the same input and the load. Okay, so that if you're looking on output here, and you understand the capacitor will be charged, discharged, and that's why the signal will be called ripple. Okay, same thing. There's a little more. And if whoever wants to know how to calculate the V ripple, right here, they get a formula here. Okay, on what the volt DC will be equal, but we not go in too much detail. Okay, and if you're looking on blue signal here, okay, what is the difference?
Big ripple, small ripple.
This will be big ripple, right?
That has a larger, that has a smaller capacitor.
Okay, that is one thing. The other thing,
Is somebody walking?
Mute the mic, mute the mic, mute the mic.
okay, now, this is a big ripple. This is a small ripple, right? So you can set the value of the capacitor bigger, will be get better ripple, correct?
Up.
One more thing. I want to know, how come this one get a big one, this one got a small one?
More discharge
Big-
time.
One's a
That
half wave,
means-
one's a full wave.
Frequency different, right? This is a low frequency and this will be high frequency. Okay, high frequency, that means the next cycle keep going. Another one low frequency, that means the period will be longer. That's why you can see. Okay, now, if you're looking on the oscilloscope on the ripple, you see this is a voltage DC. Okay, and this will be AC. Okay, so basically DC in the middle of the ripple. Okay, so you can measure from here to here. That means voltage peak.
So since the AC is above the DC, can you say that's AC riding on DC?
Right, not on, but in the middle here. You see that?
Okay,
DC right here in the middle, not on the top. When you're looking on AC coupling or DC coupling on oscilloscope. Now, I try to repeat it again. When you set up your oscilloscope to AC coupling, what they supposed to be display on the oscilloscope?
AC signal.
AC only. That means if you display AC coupling, you cannot see volt DC right here. The thing is the AC coupling will be blocked DC. If you want to see signal look like that one, on the scope, you must be set the DC coupling. DC coupling will be displayed both DC and AC. Okay, now when normally you're working on the lab, when you want to set the AC coupling,
When you want to block DC.
I understand, but I asking when you want to set it to AC coupling.
When you got the signal going into the circuit on the input.
Yeah, right now you can see the signal we show on the display. But my question is, when you're working on oscilloscope, sometimes you must be decide you want AC coupling or DC coupling. My question is, when you're working, when you want to set your scope to AC coupling.
When you're
When you
working
wanna
with
see
AC
only
signals.
AC. When you want to see only the AC. If you want to see both AC and DC, you set it to DC coupling.
Okay, now I tell you.
If there's no information in the DC signal, all the information is in the AC signal. So
Put it
that's what you
after, put it after the capacitor by the generator so you
Okay, now I show you, you get 12 volt DC, and I get 10 millivolt for AC.
No.
What your scope we get? If you're doing, you
You
know,
have to set the sensitivity so low that you won't see the AC signal if it's DC coupled. But if it's AC coupled, you can increase the sensitivity to see the AC component.
okay, go back into my question. You see the signal I display. DC, you get 12 volt. Ripple, you get 10 millivolt. What your oscilloscope you want to set? AC coupling or DC coupling?
AC.
AC.
AC, okay, why?
To be able to see the ripple, the small signal.
Perfect. The reason is, in that point, you get both DC and AC. And now you want to measure this one. If you set to DC, you cannot see it. You can see DC here, and you can see the signal look like this one. How come you measure? So that's why you have to take this guy out. That means you must be set to AC coupling. Okay? The thing is the signal, the small one will be buried inside the big signal.
Mr. Pham, I had a question.
Yeah.
So which one of the couplings, is it AC or DC? Which one of them allows you to see both AC and DC?
DC.
Okay, so DC allow you to see both AC and DC. However, in this case, you're saying because of the ripple and the smallness of the size of the signal, you want it on AC coupling.
That's why. We want to block the DC.
Okay, thank you.
Mr. Pham.
Yeah.
It also depends where you put your probe on the circuit so that you pick up both the AC and the DC signal, correct? Because if you put it before a coupler or before a capacitor, you're gonna block your DC, so you won't see it anyways.
I said, if I want to measure this signal, you must set for AC coupling. Otherwise, you see, you get a 12 volt DC here, and the signal will be too small compared to 12 volt. Then you cannot see the ripple. How can you measure? However, if you say, I set to AC coupling, they take that guy out. Okay, now, if they take that out, and now you can see the signal will be look like. The signal will be look like this ripple here will be going down here. That will be a 0 right here. No more.
No more DC.
So that's why you can change the volt per division, try to make the signal bigger. You can measure it. Okay?
Maybe a good way to look at it is to say, if you want to see the signal coupled with DC, you
Yeah.
have to set your sensitivity set maybe 5 volts per division. But then the 10 millivolts would be so tiny, you couldn't see it. But if you do AC coupling, you could set your sensitivity to 10 or 5 millivolts per division, and then you'd see the signal.
Right. But you must set the AC coupling if you want to measure the ripple. Otherwise, no way you can measure the ripple. Okay, let's see. Quick go to this thing. Gee, the time runs so fast. On that one, I want you to tell me what P we pick primary. Just quickly to go the answer so the people can record it.
Phi peak is equal to phi phi RMS divided by 0.707. So it's equal to 162.66.
That's what I got.
Okay, V primary, what you get? 163.
Yeah.
Peak.
Okay. V P. That's the answer. Okay. Now they want V secondary.
$16.3.
Perfect. 16.3 volt. You understand a ratio 10 to 1. That means you take that voltage times 1 divide 10. You get 16.3. Okay. You understand the question number C. Unfiltered peak full wave rectify voltage. That only they telling you they want to be output without capacitor.
16.3 minus 1.4.
Perfect. 14.9, right?
Yeah.
What frequency?
60.
They get a 60 hertz full wave rectify.
20.
100 and
120.
perfect. they will be double frequency. Basically, this everything will be in the handout. Please read it over and over.
Hey, Mr. Pham, so is it 120 because it's full wave as opposed to half wave?
Half wave will be the same. Half wave will be the same frequency between the in and the out. However, the full wave output will be double of the input frequency.
Okay.
Okay, good.
Mis-
Now, I want to ask.
Mr. Pham, before you move, could you please give me 3 more seconds to take a picture of the last slide, please? The one with the calculation.
Okay, let's see.
Just
Go
before,
right. Go
just
right
before
to
the end.
one. You said this one, right?
Yeah.
Okay, what happened?
Okay, I'm ready. Just I took a picture. Thank you.
You done?
Yeah, he's done.
There.
Okay, now I get some in the pad, not quite clear on this thing. I want you to do for me.
Five. 5.
That's what I want to bring it up.
Yep, 1.09 volts. There's not enough voltage to break down the Zener.
Well,
12.
The output should be 1/11
okay.
times 12.
The key point is we want to know what voltage here, right?
Yeah.
That's what we want to know.
5 volts?
Now,
12.
now.
12 volt.
Now,
Oh, wait a minute.
No,
Hold
it's
on.
I telling you
Plus,
what to do. That make a correction or misunderstand in the past.
Oh, okay.
Okay, first thing, we want to know what voltage here. Okay? In order to do it, we suppose without Zener. No Zener. Then you see what voltage here. Okay, without Zener.
11.
1/11 times 1/11 times 12.
So
1 volt.
12 times 1K divide 10K 1K voltage divider. Right?
1 volt.
Yep.
What you get?
1.1.
1.1?
Yeah.
Yep.
You get 1.1 volt here. And now, if you connect the zener, and that will be a 5 volt. Okay? So they not break down. Okay? Zener not break down. Okay? And they not on also. So they be out, open. So the answer will be VO will be equal 1.1 volt. Okay?
Mr. Pham,
Yeah.
what is it about this circuit that made you recognize what you did right away?
If you see the zener, right?
Yes.
You must know what the voltage at the anode of the zener by remove the zener. That's what I say, without zener. Then you calculate that voltage. In this case, I suppose I have a no zener there. So you get a voltage divider.
Wait a minute, the confusion is you got the zener is rated at 5 volts and the source voltage is 12 volts. So when I'm asking you, when you look at that circuit, how can you tell that you need to remove the zener diode?
Tao đáng khóc mà tao không khóc nè. Mắc gì phải khóc?
What?
I didn't understand.
Yeah, go ahead.
Because when you calculate the voltage across R1 and R2, it equals less than 5. So therefore, there would be less than the amount of voltage coming in to the zener diode to turn it on.
Okay, I was trying to talk some, I didn't get what okay. Once again, the zener is 5 volts, the source volts is 12 volts. And I'm saying, when you look at the circuit right away, how do you know what to do with this particular type?
That's what I said. First thing, no matter what the 12 volt or any voltage, you must be take the diode out first and calculate the voltage.
What that allows you to do is to calculate the voltage drop across R1.
Exactly. That means just a voltage divider.
So if the voltage drop across R1 is greater than 7 volts, then the output voltage will be less than the zener voltage, and the zener will not break down.
In this example, we calculate, we get 1.1 volt right here, right? And now I connected the zener here. Zener break down at 5, but you get only 1.1. They cannot break down. Now I said don't care about 12 volt here. We care about the voltage right at this point. Some example we give it to you, the thing is this resistor and this resistor almost the same or smaller. Now I try to change the resistor to 10K. So the drop voltage here will be bigger before they going up to this point. So finally, when you're looking at the zener, then you must know without zener, then what is the voltage here before you decide they break down or not. I given you a little thing here. I change that one. Okay? 1K. Okay, so without the zener, what the voltage?
6 volts.
6.
5 volts.
5,
Nope,
many
6
volts?
volts. 6 volts.
6 volt. Okay.
So if you attach the zener, it will break down
Right. So you get 5 volt.
and
Yes.
yeah, it will clamp the output at 5 volts.
Okay. That is a key point. I want to bring it up for you guys. Okay. On
Mr. Pham, you need to fix your screen. Look like you got 2 screens or half of one or something.
let's see, how can I fix it? No, that one, remove that one, that one. Okay. So I just give it to you. I change that one to 1K. So the voltage here, they not 1.1. You do calculation. 12, okay, times 1K plus 1K. You get,
6 volts.
so now here 6 volt. So zener break down at 5 volt. So now they will be break down. Okay, and the output will be equal 5 volt. What I want you, make sure you download on update whatever we put it in to the handout to your computer. If you can bring it out, that's good. Try to read it, highlight which one you want to memorize. Read over and over. Okay. On Wednesday, we'll be start with the bipolar transistor. I already uploaded, download and read it before the meeting. Okay. That will be helping you more understanding. Okay, so now I want you to take the quiz. Around 18 minutes maximum. Quiz number 6. You done on that one, right?
Done.
Okay, so now I will be given to you the solution for that quiz.
Wonderful.
That is the number one. If you done for copy the solution, let me know. I have one here. Let's see. I have one here. Basically, the voltage across the resistor 0.7 volt divide to R1. That's why you get 0.212 milliamp. VR2. That means you need to know what the voltage here. Okay? Voltage here will be 20 volt minus this voltage 0.7 minus this voltage 0.7. Okay? That's why you get VR2. 18.6 volt.
You say again now.
IR2 on this one will be VR2 divide R2 3.32 milliamp. And I2, that means the current here. So basically you get a current I2 and current I1, they go to R2. So the difference between those two current, then you get 3.108 milliamp. That's now telling you D2 and R1 in parallel. Okay, number 5, you get 12 volt. Number 6, Zener breakdown. You get 10 volt. So the first one don't have a zener, and two resistor R1, RL the same voltage divider. You get a half 24 volt, that means 12. And number 8, zener breakdown. So you get 6 volt. And then they want the current flow through R1. You take the difference between 24 and 6, divide to R1. Answer will be 7.2 milliamp. Okay, you want V peak, you take the VIMF divide 0.7. You get 157.14. And you want the V out, they will be V peak second divide 2 and minus 0.7 volt. If you want to know the formula, go into the handout for full
Sorry.
wave rectifier with your diode.
Sorry, Mr. Pham, but this one is V peak secondary. Shouldn't that be after you work out what is the V peak for primary? And then since it's 4-to-1, you divide by 4. So therefore the voltage should be a lot lower. Should be that divided by 4, isn't it?
That will be 110 divided to 4, right?
Right,
You get the VIMF for the second.
right. And then divide
Let's
by
see. 110 divided to 4, you get 27.5, right?
right, and then divided by 0.707 to get the V.
Divide by 0.707. So you should get 38.9.
Right, that's what I got. Thank you.
Okay. V per second. Yeah. Okay, thank you. I correct that. 38.9.
But doesn't the center tap reference the output voltage to ground? So it would be 1/2 of that, right?
You say the output here, VL. VL equal V peak divide 2.
No, he was talking about the center tap.
The center tap in here, that means you get a half of that one, right? 38.9, that means V peak second from here to here. Not from here to around here. So V peak second from here to here. If you divide it, okay, let's see. V peak second divide 2. The thing is you can get a half here and a half here. Okay? So 38.9 divide 2. You get 19.4.
So that is 19.4 to V out?
19.4 minus 0.7.
Is V out.
Right,
Yes, yes.
So that need to be corrected.
right. That's what I correct here. Okay? So you take the 38.9 divide 2. Okay,
So the answer to 10 is 19.4 or 5, depending on how you round it off. And V out is one diode drop below that, or 18.8, right?
19.4. You can get the same line or not.
Stefan, we still got to subtract 0.7 from that 19.4, correct?
15.7.
You take 38.9 divided by 2. Then you minus 0.7.
Yeah,
15.7.
so it's 18.8.
18.8 is what I got too.
You need to correct that again, Mr. Pham.
38.9 divided by 2. You get 1945
Minus 0.7
minus 0.7.
equals 18.8.
18.7.
Okay.
Depends how you round off.
Okay,
If you
so
total,
make sure you guys download the bipolar transistor. Okay, we will be stuck on Wednesday.
Okay. Okay. What's the last answer? That's number 11. What's 12? 13.
We still more, right?
Yeah, 12, 13.
Oh, okay. I thought we're done. So they now want to know voltage here and V out.
Can you scroll your screen, please?
I've got 20.6 for 12.
Hey, Mr. Pham, while you're looking, I got a question for you. When you do these circuits, are you using multi-sim 7 or P-Spice?
P-Spice. That one,
Yeah,
multi-sim.
multi-sim. Okay, thank you.
You guys will be very soon get the assignment for halfway rectified, full-way rectified with diode or bridge rectified. I'm working on that. When you can get that done, that means you really know how to using MC7 to run the full-way, halfway, or bridge rectifier.
But you shouldn't need a simulator to solve this circuit, right? You can do it by calculation.
Yeah, exactly. We don't care calculation. Everything you get a computer can do for you. then you have to know how to tell the computer to do it. So
And
that by this
also,
time you can get more and more MC7.
also with the M77, that gives you practice on how the real multimeters and oscilloscopes work.
Exactly.
I'm not getting the same numbers on number 12. I have voltage at 110 divided by 5 equals 22 VRMS, 22 times 0.7. I have 15.4, not 31.
Oh, you divide it, right?
I thought I times it. See,
You get the VRMS and you want to convert into VPIC, then you have to divide, right?
oh, okay.
I get it wrong.
But the problem is not asking for VP, it's asking for VRMS.
Okay.
So the VRMS in the secondary is 1/5 of the primary VRMS, which is 110. And then you have to subtract 2 diode drops to get the voltage, RMS voltage at 0.2.
Okay, let's see. Before I multiply. If you want to get a 3147,
43.
that means you multiply, right? 22 times 0.707, you get 15.5.
Right.
So that will be VPIC here. $15.5. Okay. And you minus 1.4.
Okay.
14.2.
Mr. Fan, why do you get 15? It's 22 divided by 0.7. That should be about 30, 31, isn't it?
Yeah, 31.4.
Yeah.
So it is multiply, not divide.
Yeah,
Okay.
so divide, yeah. So
That,
it's
that's what I'm trying to figure out. Which
Yeah, all they confused is why are we converting from VAC to VRMS, then why we converted to VPeak, and
Okay,
the answer, the final answer is VDC.
Okay. Let's see, 110 here.
Yeah.
Okay. You get
100
secondary 22.
Okay, we
RMS.
follow. Yeah, that we do
That's
follow.
RMS. That's
Okay.
Yeah, that's
RMS.
RMS
now-
value.
And now you want to get a VP.
Why do we need VP?
Why? No,
the answer you want is VDC. Why do we
Yeah,
need to
to
convert it to VP?
understand, you have to get a VP. The thing is why I asking VDC. The reason is you get a capacitor here, filter out.
Could you mute, please?
That's why you get VDC. You understand that? You get, let's say 22 divided 0.7, you get a VP. Okay?
I don't think you need to take that step. Once you get the VRMS in the secondary, then the capacitor converts the ripple voltage, the RMS value of the ripple voltage to a DC value equal to the RMS value.
You mean you don't need a VP here?
No, I don't think so.
Okay. How come you can see that on the scope with a ripple on the top? You're telling me, if you say you want to get a VIMS here, how come you can see the VDC on oscilloscope with a ripple on the top.
If you remove the capacitor, you'd have a.
No, I said the capacitor here. I'm not removing.
What I'm saying is, if you remove the capacitor, you would have
Okay,
a.
if you remove, then you have to using the meter to measure VRMS.
Could you mute the mics, please, Mr. Fan, so I can hear?
All I'm saying is that the RMS voltage of an AC signal, a compound signal with an AC and DC component, the RMS voltage is equal to the equivalent DC voltage. And the capacitor converts the compound voltage to the equivalent DC by filtering out the ripple. That's all I'm saying.
Okay, anyway, you have to get the same answer, no matter what you want. But what I'm saying is, right now, we're working with the oscilloscope to measure the function.
So at that point, that 22 RMS or whatever should be multiplied by 0.7, not divided to get the 15.5.
No, the first thing you must be see the peak first. I show you on this thing here.
I think the right answer for 12 is 20.6 volts DC.
see
And
that?
the right answer for
You see
13
on
is
that output, you can see this is the peak here. And this is the ripple.
Right.
Okay, so you have to measure from here to the here. That will be a V peak. Okay, and now they get the capacitor. That means in the this one will be a DC. So basically, this will be get a DC. You know, with the one peak with the ripple, and that will be a DC right here. And let's see. First thing we have to find out what V peak equal. Okay, and they will be minus 1.47.
So if you take the 22 divided by 0.7 volt, the answer should be 31.4 volt
Okay.
peak.
Let's see. 1222
Yeah, I agree with that, Sam.
divide to 0.7.
I second.
You get 31.1.
31.4.
31.43. 31.43.
Okay.
Okay, that's the same. 31.43.
0.43.
Okay, 3. Okay,
And then minus the 1.4 comes
minus
to
1.4.
30 volt.
Okay.
Yeah, 30.
Let's see, 31.43 minus 0.7 equal minus 0.7.
30 volt peak.
Yeah. 30 volt DC.
But the quiz is not asking for peak voltage, it's asking for VGC, which implies
The
RMS
thing is, if you
output.
don't know V peak, then you cannot get the VDC. If you're looking on the scope like I just showed you. If you don't know volt from here to here, then you cannot get that the DC. If you get a flat here, no ripple. So that means the DC. But the calculation, then you have to know what the V peak in here. That's the same thing VDC. The thing is, you get a capacitor here.
I think I'm going to end up building this circuit when we get off the air and then see how it works then, huh?
Yeah, you will be seeing this circuitry in the assignment.
Well, I'm gonna see it a lot sooner because I'm gonna have to do it tonight.
Oh, okay.
Don't sleep late, Mr. Smith.
You better make
And
some
Joseph,
coffee.
Joseph,
you see that? Voltage
Joseph,
out,
I think you'll find,
12 volt, they will be break down. So that's why they get 12 volt. That should be on VDC. When they come
Hey, Joe.
down here, okay, without the capacitor, you can get a VP. However, if the capacitor here, they will be turned out to be DC with a ripple on the top.
Somebody was trying to tell me something. Go ahead.
yeah, Joseph, I think you'll find if you simulate the circuit, you'll see that the capacitor converts the RMS voltage of the AC of the ripple current to the equivalent DC value, which is equal to the RMS value of the AC current.
Okay, I'll play with it tonight. I'll stay up all night.
No, don't do that.
No, I am.
Good luck on that, Mr. Smith.
Now, you guys got me interested in this now. I'm going to try to find out what's going on.
You better start your coffee pot.
Hey, thanks, guys. Thanks a lot.
All right, thank you.
Are the
Thank you so much.
Thank you.
Okay.
Bye-bye.
Are we going with these calculations in? Is this what we're working?
No, hold on.
Thank you, everyone. Have a good night.
Hey, Lowell, I thought you was the capacitor man in the first place.
Hey, I got Faustat going, so I'm just working with whatever the calculations are here. So
And what about the Faustat?
that's up to Mr. Fan.
No, you do it.
And I'd like to invite anyone who's interested to join the study group tomorrow for a discussion of this topic.
Okay, so we'll be done. Hello, Lou.
Okay, thank you.
All right, good night, Mr. Pham.
Were you talking to me, Mr. Fan?
Good night.
I asked you about your program for PSPI. You bought it?
I have MSIM 14. Do you want me to design the circuit and have it ready?
Yeah, please. Also, can you send me the name of that PSPI so I can buy it?
Well, it's the Multisim 14 through Studica. If you prove you're a student, you get it for like $40.
Okay, Multisim 14, right?
Yeah, it's MSIM 14. It's not MSIM 7. It's MSIM 14. It's
No, I know PSPI, 14
but
for student.
it's MSIM, not PSpice.
Right, I understand.
Right.
It's 14.2, and I downloaded it, but I had a real problem with getting the license to activate.
Just register at their website.
Okay. So
The other thing too, Mr. Pham, is remember Faustad? Remember the animation? I can build the circuit, have that ready for tomorrow also.
Okay.
I'll just have it ready and I'll let you know. If you want to look at it, then we'll talk tomorrow.
Okay.
Enjoy your evening.
Good evening. Okay. Good night, everyone.
All right, get a good night's sleep, Mr. Pham, off of this.